Picture this. It's 2 a.m. A military helicopter is flying high over these incredibly dense, dark mountain ranges. Everything is totally normal, until suddenly, the entire aircraft just starts shaking violently. Out of nowhere, warning alarms are absolutely exploding inside the cockpit, and the pilot is frantically trying to figure out how this incredibly advanced machine is just losing complete control. Things went from bad to catastrophic in the blink of an eye. Within seconds, this multi-ton, super heavy machine literally lost its battle with gravity. It began falling rapidly toward the ground. The engines had completely failed. At this point, it's basically just a doomed, falling rock. But then, something unbelievable happened. At the very last possible moment, the helicopter avoided a deadly crash. So what exactly saved it? Well, to figure that out, we have to ask some big questions. How does a helicopter engine actually work? Where does the rotor get all that power? Why does a chopper spin out of control if the tail rotor fails? And crucially, if the engine completely stops, why doesn't the whole thing just instantly
Our
smash into the
helicopter
ground? In
details
this explainer,
are
we're
very
going to break down the
good
full
and you
technology behind
support the
helicopter engines,
channel.
step by step.
Please
From the air
subscribe
intake and
and
compressor,
like and
right
share
through to
the
the combustion
video.
chamber, turbine, gearbox, and finally, the incredible emergency auto-rotation system that has saved countless lives. By the end of this, you'll know exactly how one of the most powerful flying machines on Earth truly works. All right, part 1. Inside the turboshaft engine. Let's dive right in and see where the real magic happens. So a lot of people look at a helicopter and assume those giant spinning blades on top are the actual engines. But those are just the main rotors. The true heart of this beast is hidden deep inside. Now, back in the early days, older helicopters actually used piston engines. Believe it or not, these were super similar to the engines in old cars. Cylinders, pistons, spark plugs, the whole shebang. But as helicopters got bigger and heavier and needed to lift massive payloads, car engines just didn't cut it anymore. Engineers had to develop the modern turboshaft engine, which is incredibly compact, highly efficient, and capable of generating just massive amounts of rotational power. Now, you might be thinking, wait, doesn't a turboshaft look exactly like a jet engine on a regular airplane? And yeah, they're definitely related, but they do completely different jobs. A jet engine's main purpose is to create forward thrust, basically pushing air out the back to rocket the plane forward. But a helicopter's turboshaft engine? It's designed to create rotational power. It's not pushing the chopper forward. Its entire job is to aggressively spin the components connected to it. To understand how it does this, we have to look at how the engine breathes. It's a 4-step sequence that completely relies on a continuous flow of air. First, the air inlet captures the outside air. Second, the compressor radically builds up the pressure. Third, the combustion chamber introduces fuel and ignites it. And fourth, that expanding heat spins the turbine. Literally, without this constant, rapid intake of air, the engine couldn't generate a single ounce of power. Let's zero in on that second step for a second, the compressor. Its job is to take all that incoming air and massively squeeze it, bumping up the pressure before it even touches the fuel. Some engines use what's called an axial compressor, which uses high-speed blades to push air straight through in a line. Others use a centrifugal compressor, which violently spins the air outward to ramp up the pressure. Either way, creating this high-pressure environment is the absolute secret to burning fuel with maximum efficiency. Which brings us right to the combustion chamber. When that incredibly pressurized air mixes with the fuel nozzles and meets the spark, it ignites. But, and this is key, it's not some huge bomb-like explosion. Instead, it's a continuous, perfectly controlled burn. This relentless fire creates superheated gases that reach blistering temperatures of over 1,500 degrees Celsius. Honestly, it's like a contained inferno in there. Moving on to part 2, generating rotational power. So how exactly do we turn 1,500 degrees of pure heat into actual mechanical flight? Well, those superheated gases have absolutely nowhere to go but aggressively backward. As they rush to the rear of the engine at supersonic speeds, they slam into a series of turbine blades. This immense thermal force spins the turbine incredibly fast. And because the turbine is rigidly attached to a long rotating shaft called the power shaft, this is the exact moment where that raw heat energy officially transforms into the mechanical rotational energy the helicopter desperately needs. But here's where we hit a massive engineering roadblock. That turbine inside the engine is spinning at unbelievable RPMs. So you might be wondering, why not just hook that spinning shaft directly up to the big main rotor blades on top? Take a second to imagine that. If you actually did that, those heavy rotor blades would spin so insanely fast that the physical forces would literally tear the entire machine apart in midair. No way that works. To solve this, engineers came up with a vital middleman, the main gearbox, or transmission. The gearbox takes that ridiculously high, frankly destructive rotational speed from the engine and gears it way down. It radically reduces the RPMs into a totally controlled, perfectly safe speed that those heavy main blades can easily handle without shattering into pieces. Part 3. Steering and stability. Okay, so now we have a safe, powerful spinning force. Let's see how that power actually interacts with the air to make this thing fly. The main rotor system is made up of the blades, the hub, and the swash plate. If you've ever looked closely at a helicopter blade, you'll notice it isn't completely flat. It's actually shaped exactly like an airplane wing, using an airfoil design. As the gearbox spins these massive blades, their specific shape causes low pressure to form on top and higher pressure to form underneath. That pressure difference is what creates lift, that invisible, magical upward force that actually drags a multi-ton machine right off the ground. But of course, physics always has a catch. Enter Sir Isaac Newton. Newton's third law states that every action has an equal and opposite reaction. Because that massive main rotor is spinning violently in one direction, the actual body of the helicopter naturally wants to twist and spin in the exact opposite direction. This intense twisting force is known as torque. To stop the helicopter from spinning around like a crazy top, we use a tail rotor, sometimes called an anti-torque rotor. Its entire job in life is to push air sideways to counterbalance that twisting force, keeping the whole helicopter pointing straight. So what happens if this tail rotor suddenly breaks or fails? Well, without it, the torque totally takes over and the helicopter instantly begins spinning in uncontrollable circles. Assuming our tail rotor is doing its job, how does the pilot actually steer this beast? They use two main controls. First is the collective control, which increases or decreases the lift of the entire rotor all at once. That's what makes the chopper go straight up or straight down. Then there's the cyclic control. This actually tilts the entire spinning rotor disc in different directions. You tilt the disc forward, the chopper flies forward. Tilt it sideways, you drift sideways. It's brilliantly simple. As you can probably guess, keeping this delicate, high-speed balancing act in the sky is absolutely brutal on the machinery. I mean, the 1500-degree heat means you need incredibly complex cooling systems. Constantly fighting gravity burns massive amounts of heavy fuel, and the extreme vibrations from all those moving parts cause severe metal fatigue over time. It is literally an environment of constant, extreme physical stress. Which brings us to part 4, surviving engine failure. And this takes us right back to our terrifying opening scenario. Let's head back to 2 a.m. in the freezing dark over those mountains. The alarms are screaming. The engine has completely died, the turbo shaft is dead, the combustion chamber is cold, and the gearbox has zero power to transfer. The helicopter is falling fast. So let me ask that central question one more time. If the engine completely stops, why doesn't the helicopter instantly crash into the ground like a rock? The answer is a brilliant, life-saving physical phenomenon called autorotation. When the engine dies and the helicopter starts plummeting, air naturally rushes upward through the main rotor blades. Because of the special aerodynamic shape of those blades, that upward rushing air catches them and actually forces them to keep spinning on their own. Zero engine power required. The pilot quickly disconnects the dead engine from the rotors, essentially turning this falling rock into a giant glider. Those freely spinning blades create just enough lift during the drop to allow the pilot to pull off a controlled, survivable emergency landing. And that is exactly what saved our pilot in the mountains that night. Honestly, it is nothing short of incredible. As our source material points out, the helicopter is a brilliant fusion of aerodynamics, physics, and engineering. It's a machine that doesn't just casually float in the air. It actively fights to stay stable. It conquers the intense torque of its own power, and it literally has built-in physics that give the pilot a fighting chance, even when absolutely everything goes wrong. We look up and see these things flying overhead all the time, and we rarely stop to think about the violent, brilliant ballet of physical forces happening inside that metal shell. Which leaves us with a pretty fascinating thought to ponder. What other seemingly impossible machines are we entirely taking for granted that are secretly using the laws of physics to keep us alive every single day? Thanks so much for joining me on this explainer. Keep asking questions, and I'll see you in the next one.